Hey guys, here. The ocean is full of mysteries, and one of the most interesting aspects of it is what lies beneath its surface, especially at the deepest parts where sunlight cannot reach. While we have mapped out much of the landmass on Earth, only about 20% of our oceans have been explored. With such a huge area left to be discovered, researchers are continuously working to learn more about the world beneath the waves. And recently, they have been exploring hydrothermal vents in the deep sea. These vents often reveal strange and fascinating life forms that have adapted to survive in extremely hot water, complete with its own unique ecosystem, food chains, and sources of energy. Some of these underwater volcanoes have even been found to host entire cities of crabs. So, what exactly are these vents? What can we learn from them? And how do they support life? Join us today as we explore Earth's mysterious deep-sea hydrothermal vents. The Mariana Trench is the deepest known part of the Earth's oceans. It is a crescent-shaped depression in the western Pacific Ocean that stretches for about 2,500 kilometers. At its lowest point, the trench reaches a depth of about 11,034 meters. This is so deep that if Mount Everest were placed at the bottom of the Mariana Trench, the mountain would still be over 2 kilometers below the surface. The pressure at this depth is over 1,000 times greater than the pressure at sea level. In addition, temperatures at the core of the trench reach around 400 degrees Celsius. This extreme environment makes it uninhabitable for most life forms. But surprisingly, the edges of the trench host a variety of marine organisms that have adapted to survive in such harsh conditions. The Mariana Trench is also home to many hydrothermal vents, which are openings in the seafloor that emit hot water. These vents are formed when seawater seeps into the cracks in the seafloor and is heated by the Earth's core. The hot water then rises back to the surface through the cracks, creating vents that spew out minerals and other substances. Underwater volcanoes or seamounts are also found on the seabed, but unlike traditional volcanic mountains, these submerged giants don't create large eruptions. Instead, they spew out lava that cools quickly upon contact with the surrounding water, forming vast plains of igneous rock known as guyots. These flat-topped seamounts rise from the ocean floor and are remnants of ancient volcanoes that once grazed the water's surface. As erosion has worn them down over time, some now lie dormant hundreds of meters below sea level. Despite their inhospitable appearance, these volcanoes are actually home to diverse ecosystems supported by chemotrophic bacteria. These bacteria harness energy from chemical reactions rather than sunlight, forming the basis of unique food chains that support larger animals such as tube worms and mussels. While volcanic activity is a major force in shaping the physical features of the seabed, it also plays a crucial role in supporting life in deep-sea hydrothermal vents. Volcanic activity releases chemicals such as hydrogen sulfide, methane, and ammonia, which can be used by certain bacteria as a source of energy. These bacteria are known as chematotrophs, which form the foundation of the food chain in deep-sea hydrothermal vent ecosystems. In fact, many deep-sea organisms rely on chemotrophs for their energy needs. For example, tube worms have a symbiotic relationship with chemotrophs living inside their bodies, providing them with the energy they need to survive. These chemotrophs oxidize sulfur compounds released from the vents and use the resulting energy to produce organic matter. In turn, the tube worms provide the chemotrophs with a habitat and protection. In addition to tube worms, other organisms such as mussels, clams, crabs, and shrimp also thrive in deep-sea hydrothermal vent ecosystems. These organisms are able to survive in such harsh environments thanks to the presence of chemotrophs. By feeding on chemotrophs or other organisms that consume them, these animals obtain the necessary nutrients to survive despite the lack of sunlight and the toxic chemicals present in hydrothermal vents. Even larger animals such as fish and sharks can be found in some deep-sea hydrothermal vent ecosystems. For example, The Japanese spider crab has been known to live near hydrothermal vents, where it feeds on the bacteria and other organisms that live there. Hydrothermal vents are also important for the cycling of nutrients in the deep sea. The chemicals released from vents, such as iron, manganese, and zinc, are essential nutrients for many deep-sea organisms. These nutrients can also support the growth of phytoplankton in the surface waters above hydrothermal vents. This phytoplankton forms the base of the marine food web and supports the entire ecosystem in the area. The first discovery of deep-sea hydrothermal vents was made in the 1970s, when scientists aboard a research vessel in the Pacific Ocean noticed a strange underwater mountain range. Further exploration revealed that the mountain range was actually a series of volcanic vents emitting hot water and supporting a unique ecosystem of bizarre creatures. Since then, scientists have discovered numerous hydrothermal vent fields around the world, each with its own unique characteristics and inhabitants. One of the most well-known deep-sea hydrothermal vent fields is the East Pacific Rise, located in the eastern Pacific Ocean. This vent field is about 8,000 kilometers long and spans a vast area of the seafloor. It is home to a variety of vent types, including black smokers and white smokers, named for the color of the smoke-like plumes they emit. These vents support a diverse community of organisms, including giant tube worms, mussels, and crabs. Another notable deep-sea hydrothermal vent field is the Mid-Atlantic Ridge, which runs for over 60,000 kilometers along the middle of the Atlantic Ocean. This ridge is a divergent plate boundary where two tectonic plates are moving away from each other. The Mid-Atlantic Ridge supports a variety of vent types, including the rare ultramafic vents that emit low amounts of carbon dioxide and methane. These vents support a unique ecosystem of microorganisms that play an important role in the global carbon cycle. The study of deep-sea hydrothermal vents has revealed that these extreme environments can support a wide variety of life forms, challenging our understanding of the limits of life on Earth. Scientists have found that many of the organisms living near hydrothermal vents are extremophiles, meaning that they can survive in extreme conditions. For example, some bacteria have been found to grow near the volcanic vents that produce highly acidic or alkaline fluids. These bacteria are able to survive in such harsh conditions due to the presence of special proteins and enzymes that allow them to function properly. Additionally, scientists have found that some deep-sea organisms, such as the Japanese spider crab, have developed efficient ways to remove toxic substances from their bodies. This allows them to live in areas where the water contains high levels of toxins, such as hydrogen sulfide. The study of these extremophile organisms has provided valuable insights into the adaptability and resilience of life on Earth and has raised new questions about the potential for life on other planets. In recent years, scientists have also explored the potential applications of organisms living near deep-sea hydrothermal vents. For example, the enzymes produced by bacteria that live in highly acidic environments have been found to have potential uses in industrial processes that require extreme conditions. Additionally, the study of deep-sea organisms has provided valuable insights into the potential for life on other planets. For example, the fact that some organisms can survive in extreme conditions such as high pressure and temperature has led scientists to believe that similar organisms may exist on other planets such as Jupiter's moon Europa, which is thought to have a subsurface ocean. By studying deep-sea hydrothermal vents and the organisms that live there, scientists are constantly learning more about the amazing adaptability and resilience of life on Earth. They are also discovering the potential applications of this knowledge in fields such as industry and astrobiology. Thanks for watching. If you enjoyed this video, please like and subscribe to show your support. We always appreciate your support and hope that you continue to enjoy our videos.